In 2023, a robot built by Boston Dynamics fell over trying to open a door. Not because of a software glitch or a power failure, because the floor had a slight incline it hadn't been told about. That same year, a toddler in Boston navigated an icy sidewalk, a crowded subway car, and a pile of toys on a staircase, all before breakfast. For 70 years, engineers have been trying to close that gap. In the last 18 months, something fundamental has changed, and the people building these machines are using a word they've avoided for decades. They're calling it intuition. The reason this matters now is not theoretical. Goldman Sachs published a report in early 2025 projecting that humanoid robots will be a $38 billion industry by 2035. That number has since been revised upward twice. But the more immediate pressure is in the labor market. The United States is currently short 3.8 million manufacturing and logistics workers. That gap is structural. It will not close through hiring. Warehouses, hospitals, construction sites, and elder care facilities are all running the same calculation. The work that needs doing requires bodies that can move the way human bodies move. Wheeled robots can't climb stairs. Fixed-arm robots can't navigate a cluttered room. The entire premise of replacing human physical labor rests on one unsolved problem: getting a machine to move the way you do. For most of robotics history, motion was a programming problem. Engineers told a robot exactly where to put its foot, exactly how much torque to apply to each joint, and exactly how to recover from a deviation. This approach, called model-based control, worked reasonably well in controlled environments. Car factories, conveyor belts, spaces that never changed. But the real world is not a car factory. Every surface is different. Every doorway has a slightly different threshold. Every staircase has a slightly different riser height. The model-based approach required engineers to anticipate every possible variation in advance, which is essentially impossible. Think of it like trying to teach someone to drive by writing down every traffic scenario that could ever occur. The list never ends, and reality always finds an edge case the list missed. By 2020, the dominant paradigm in robotics motion was still brittle, expensive, and deeply dependent on the environment being predictable. That was the wall. The wall started cracking in 2021 when a team at ETH Zurich used a technique called reinforcement learning to train a quadruped robot named Animal to walk across terrain it had never seen. Not by programming each step, but by letting the robot fall thousands of times in a physics simulation and learn from each failure. The result shocked the field. Animal could recover from kicks, navigate rubble, and handle slippery surfaces, not because anyone told it how, but because it had internalized the physics through millions of simulated failures. In one demonstration that circulated widely in robotics research communities, the robot was pushed hard enough to go nearly horizontal, and it recovered without a single pre-programmed recovery routine. What it had developed was something that looked, functionally, like balance intuition, but that was still a four-legged robot. Bipedal motion, the kind humans use, is a far harder problem. Two legs are inherently unstable. Walking is, technically, a controlled fall. The breakthroughs with quadrupeds pointed toward a method that might finally crack bipedal locomotion. Here is the part that overturns the assumption most people bring to this topic. The breakthrough in bipedal robot movement did not come from building better hardware. It came from throwing away 20 years of assumptions about how to train software. In 2024, Figure AI and Agility Robotics both demonstrated humanoid robots that have been trained almost entirely inside simulated environments. Billions of simulated hours of walking, stumbling, recovering, adapting. Figure's robot, called Figure 01, logged the equivalent of 100,000 hours of physical practice before it ever touched a real floor. A human elite athlete trains roughly 10,000 hours to reach peak performance. This robot compressed 10 times that into weeks of compute time. When Figure 01 was deployed in a BMW manufacturing facility in Regensburg, Germany, in late 2024, it adapted to real surfaces it had never physically encountered, because the simulation had been deliberately randomized with imperfect floors, unexpected friction coefficients, and random perturbations. The robot had been trained to expect the unexpected. That is the fundamental inversion. The old approach tried to predict every scenario. The new approach trains the robot to be wrong constantly and recover anyway. The mechanism that makes this work is called sim-to-real transfer, and understanding it explains why the last 2 years have felt like a step change. Inside a physics simulation running on a cluster of GPUs, a robot body attempts a walking task. It fails. The reinforcement learning algorithm adjusts the weights in the robot's neural network slightly, rewarding movements that kept it upright longer and penalizing collapses. This loop runs millions of times per hour, something no physical robot could survive, because real hardware would shake itself apart. The analogy that makes this click: imagine you could practice riding a bike by running the experience in your mind at 10,000 times normal speed, and each mental crash instantly told your nervous system exactly what adjustment to make. You would learn in an afternoon what normally takes weeks. The counterintuitive element is what engineers call domain randomization. Rather than simulating the real world precisely, they deliberately make the simulation messy and inconsistent, varying surface friction, joint stiffness, sensor noise, and gravity itself by small random amounts. This seems like it should make learning worse. It actually makes the resulting policy more robust, because the robot never learns to depend on any single consistent physics. It learns principles, not recipes. The complications are real, and the people building these systems will tell you that if you ask them directly. First, sim-to-real transfer is not perfect. There is always a gap between simulated physics and actual physics, and in bipedal locomotion, that gap can be measured in falls. Tesla's Optimus robot, which entered limited factory trials in 2025, required significant hardware intervention after early real-world deployments revealed unexpected failure modes the simulation had not captured, particularly around dynamic loads, meaning carrying things while walking across uneven ground. Second, there is a deeper problem nobody has cleanly solved: hands. Locomotion is advancing rapidly. Dexterous manipulation, picking up a raw egg without breaking it, folding a shirt, turning a door handle at an unexpected angle, is still enormously difficult. Most humanoid robots today are, bluntly, clumsy with their hands. Third, and this is the one that rarely gets discussed in press releases, is energy. The human body is extraordinarily efficient. A humanoid robot performing equivalent physical tasks currently uses roughly 4 to 6 times more energy per hour than a human doing the same work. For you specifically, the timeline to watch is 2027 to 2030. That is the window in which robotics analysts at Morgan Stanley and Deutsche Bank both project humanoid robots will move from controlled industrial pilots to genuine scaled deployment. The industries that will feel it first are logistics, warehousing, and light manufacturing. Meaning if you work in fulfillment, assembly, or materials handling, the disruption is not a decade away. It is arriving during your current career. Elder care and physical rehabilitation are the second wave, projected for 2030 to 2035, and that wave may actually be welcomed. There are not enough caregivers globally to meet aging population demand. What you can concretely watch for: when a major retailer publicly announces a humanoid deployment contract exceeding 1,000 units, that is the signal that the technology has cleared the cost threshold. That announcement has not happened yet. It is likely within 18 months. Zoom out for a moment and consider what has actually happened here. For 7 decades, engineers tried to teach robots to move by describing motion. The breakthrough came when they stopped describing and started letting machines discover. That is not a small methodological shift, it is a philosophical one. And it mirrors almost exactly how humans learn to walk, not from instructions, but from falling, recovering, and building an internal model of the world through experience. The next 10 years will determine whether that learned intuition can extend beyond walking into the full range of human physical capability. If it does, the $38 billion